Good morning, everyone. So I said that this third day is about industry in terms of domains. So this morning we'll have two sessions, one called Domain Interoperability, and the other one is about harmonization. And in the afternoon, we'll have two sessions also on ontology validation and also tools. We have also a keynote speech from Bosch. So from Alessandro Ottarmani. So this the plan, and in parallel, as you know, that there is the prototyping lab running. So hope that you enjoy the day, and I will invite Arko to chair the first session and introduce the speakers.
Yes. Okay, thank you, Hedy, and I welcome you all on the first session of day 3. So the first session is focused on the domain ontologies, the interoperability issues, and also the harmonization strategies. In the first session, we have some exciting speakers. Professor Barry Smith will we'll have a session in the beginning. Then we will have. I'm sorry. So for the morning we will have 2 sessions. In the first session, which is I am sharing, will be on the domain interoperability and harmonization. Then we will have a coffee break, and then we'll go for the second session. In the first session, we got speakers such as Barry Smith, and then Sylvia will present some recent updates on our work package 3, which is focusing on the domain ontology. So it is very much relevant to this session. But then we will bring in 2 more speakers, David Cameron and Francesca Blanket. So I'm bringing in the first speaker, Professor Smith, and he doesn't need any more introduction, and I will give the stage to him. Yes.
Thank you. So this is a strategy for domain interoperability. And let me just explain the problem, which I introduced already yesterday. So you have 6 or 16 different groups in different parts of the world, 4 of them represented here in this meeting, all of them interested in developing domain ontologies for the area of, let's say, additive manufacturing. If they don't talk to each other, then most of them are reinventing a wheel. If they don't talk to each other, most of them will miss important links to other kinds of data, which will have to be created later, and which will almost certainly mean that their ontology is already redundant because there's no way of making those necessary links. So the idea is that if you want to create ontologies for an area like additive manufacturing or any area in industrial engineering, then you need to try and create coordination between all the groups or all the serious groups or all the groups you can find who have an interest in building one or other or several of those ontologies. Now that's what we've been doing in the Industrial Ontologies Foundry. So we have several, we call them working groups devoted to specific areas. We have further efforts to identify people who might be interested in creating further working groups. And I'll mention at least one opportunity along those lines that's already been discussed at this meeting. All right, so this is the IOF core. The IOF core is intended to be a rather small, highly general ontology, which deals with the definitions of terms which everyone building domain ontologies in the industrial manufacturing domain will need. Terms like manufacturing process, And I'm going to go through bits and pieces of this ontology and address problems that we are already attempting to solve, problems that we need help with solving, and problems which will throw light, I believe, on the general processes involved. So there are two kinds of entity or two kinds of class in the IOF core. On the one hand, there are all the relevant BFO classes. And then on the other hand, there are children or children's children of those classes which are introduced because they are specific to the IOF domain. And so we have, for instance, we have various kinds of processes, manufacturing processes in the strict sense, business processes, and so forth. And we need to have hooks for various ontologies dealing with these different kinds of processes. So manufacturing production process, we have a working group dealing with that. Supply chain processes, we have another work group dealing with that, and so forth. And now manufacturing process goes hand in hand with various kinds of measurement process. And I think measurement process is an interesting area which points to some of the advantages of working within the IOF. First of all, in order to have a good ontology of measurement processes as they occur within a factory, we need to have a link to some ontology of units of measure. And there are about 4 units of measure ontologies. All of them have some good content, but all of them have problems one way or another. There are quite general problems working within the BFO framework in dealing with the more obscure units of measure, like energy consumption, which presumably we will need to have a treatment of. This is an area where BFO is at the moment working quite actively as part of our efforts to build a physics ontology. So that's one area where once we have a good units of measure ontology plumbed into the IOF system, this will add to the opportunities for people using the IOF to deal with measurement data relating to manufacturing processes. Now we have lots of information about the properties of materials, many of which are also captured using units of measure. They are results of experiments. And so we're going to need to link to an ontology of materials attributes, materials processes. And I am still hoping that the EMMO effort is going to provide the necessary content. And but then there are areas where we're measuring things in manufacturing which don't relate to units of measure. And an example would be tolerance. So many kinds of manufacturing process depend very, very strictly on understanding the tolerance of the equipment that you're producing. This is a legal requirement if you provide equipment for the Department of Defense, for instance. And so we're going to need ontologies which deal with things like tolerance. Now, one central feature of, let me see if I can remove this thing. One, not that it's going to make a big difference. Well, just as a message up there.
No, it's
okay, good. So one central feature of the IOF, and you might think of this as a design pattern, is that we are interested not in any process which take place inside a factory. So we're not interested in processes involving catching mice or sweeping mice droppings, because they're not planned processes. So the planned processes are processes which are specified in planned specifications. And so we have a quite elaborate ontology of what it is to have a planned process and the accompanying planned specification, all of which make the building of the ontology interestingly and usefully uniform. Now, some people want to go further than that. So Michael Gruninger, who's been mentioned already in this meeting, he works in ontology development where OWL does not really play a role He's using first order logic, common logic exclusively, and he's doing that in a very mathematically precise way. And he has a vision of the future factory. I think Dimitris has a vision like this also. The future factory is a mathematical entity. So we'll be able to model what goes on in the factory mathematically, and we'll be able to produce simulations mathematically of what happens in the factory if we do this or that. I am much more modest in my expectations. I don't think that we will, I don't think we're close to having the kind of mathematical model of manufacturing that Gruninger believes in, but an illustration of where this plays a role is in the process specification language. When we started the IOF, we had a quite long and involved decision process as to which would be the top level ontology of the IOF. And we had three competitors. One was BFO, one was PSL, and the other one was some Italian thing. And BFO was decided, again, by a long decision process, that it would be the ontology which is accepted. And but PSL still plays a role in occasional extensions of the IOF. All right, now, as some of you know, I published with my co-author, Job Slankreber, last September, a book on AI. It's a book on the limits of AI. And the central thesis of the book is that there are two kinds of systems. There are, on the one hand, engineered systems, if you like, simple systems, illustrated by every engineered artifact. And all such simple systems are such that we can predict their behavior mathematically. But that's what we do in the design phase. When we're designing a new artifact, then we work out the mathematical properties of the parts, of the output, and so forth. And then we start building it, and we test it until we reach a point where we can actually create a product. And so AI works very well for simple systems. But most systems in reality are complex systems. And that means you can't predict their behavior. We can't predict the weather. We can't predict how CERM will feel in 5 minutes, whether he will smile when I mention his name. He does smile, you see. But nobody could predict that. So the traffic system is a complex system. All of these are systems whose behavior, and this is the main topic in the book, whose behavior makes mathematical prediction impossible. And so AI systems which try to emulate these behaviors are going to have to use approximations, and these approximations will contain a high risk of being wrong, and therefore they won't be able to be used for mission critical things. And maybe even driving a car is a mission critical thing. We want to be able to trust our car. And so that Michael Gruninger's idea is that the factory itself is a critical system, is a simple system. Now, I think that maybe in the future, there will be factories without human beings in them. Maybe factories without either human beings or mice in them. So they'll be sealed off. They'll be like big artifacts. We're not there yet, but this is an idea which some people embrace. And if that idea works out, then the business processes in the factory will be modelable mathematically. But those business processes in the factory are part of a much bigger system, which includes the stock exchange and the price of currency and the price of metals, all of which belong to complex systems. And so the real world business processes are always going to introduce a complex system feature in the manufacturing process, because they're going to determine how we model our production on the basis of the costs of materials and transport and so forth, and investors' interests and so forth. All right, now we have a working group on systems engineering, And people are welcome to join any of these working groups. Typically, they meet once every 2 weeks for hourly phone calls. And between the phone calls, people develop new contributions to the relevant ontologies. And then we have a lot of information content entity classes in the IOF core, each of which points to a whole family of new ontology content, which we are planning eventually to build, but which we mostly are still waiting for volunteers to create working groups to do the work of building those specific information content entity areas. So human resources contracts, for instance. I'll come back to that in a minute. So BFO has what we think is a pretty robust treatment of information content entities, which means data, the contents of documents, the contents of emails, and so forth. But there are areas where we need a treatment of other kinds of digital or abstract, non-material entities, which we don't have a treatment for. One of them is rights. Now, as manufacturing becomes more and more a process of manufacturing digital artifacts like software, then it will become the fact will become more and more important that we don't sell software. We sell rights to software. And so the IOF is going to have an ontology of rights of the sort which people buy and sell. Yes, Dimitri.
Don't forget it. So with the cat IP, we can
Oh yeah, absolutely. So one, yeah. So yeah, one of the working groups that may be spawned by this meeting is a working group on IP. So the ontology of IP, that there is already a draft ontology of IP, and if things work out well, then that draft will become the subject matter of a working group at the IOF. But in order to deal with these issues properly, we need a wider ontology of law, and that will not be part of the IOF. Now, we have people working on that topic also, and the idea is that we coordinate. So the work on rights, property, and so forth within the framework of the IOF should be consistent with the more general work on rights in general that is proceeding in the ontology of law field. All right, now, one problem with BFO, people say, is that we can't deal with non-existent entities. And we say, that's great. Who would want to have an ontology of non-existent entities like Father Christmas or, I don't know, Hamlet? And there are people working in literary theory who think we need an ontology of fictions. Now, BFO has a way of dealing with this. So we just don't, we're realist. And what that means is that all the classes in BFO are required to have instances. Now, we don't say when the instances have to appear. And so if somebody is designing an oil platform, and it's already got a number and a location and a job description and so forth, the oil platform doesn't exist yet, but we can already describe it using the terms of the IOF because we know that it's on the way to existing and there's only one of them. And so that class already has let me start again. That class is already such that there will be an instance of it. And so, but that solution doesn't work generally. So the more general solution that we are recommending at the moment for dealing with non-existent objects, for instance, with molecules which have never been synthesized and which may never be able to be synthesized, the more general solution to that is a very simple solution, which is called, actually, this is a misspelling, modal, M-O-D-A-L, relations ontology. And the idea of the modal relations ontology is that if you have an area where you're dealing with non-existent entities, like, for instance, non-synthesized molecules, then you use BFO exactly as it is, and you use all the relations of BFO exactly as they are, but you use them in such a way that one of the relata doesn't have any ontological commitment. And so you can make all the statements that you want about your non-existent oil platform, for instance, but you can't infer from those statements that the oil platform exists, which is exactly what we require. Now, we are not, the modal relations ontology solution is not yet fully mature. And I'm sure that we will improve it, maybe even replace it by something quite different. But we do have a solution which is intuitively the sort of solution that we might need. All right, now let's look at roles. Actually, first let's look at capability. So capability is not a term in BFO, but we are going to be adding it one way or another. It's certainly a term in the IOF. And capabilities are like functions in the sense that we can build, design, create an artifact to have a capability, just as we can build it to have a function. But the function is a special kind of capability. The function is the reason why we build it. So we create screwdrivers in order to transmit cork from the screwdriver to a screw. That's the reason why we make screwdrivers. But the screwdriver may work for 7 different kinds of screw. That's a capability. It's not the function. The function is to transmit torque. The capability is to be able to screw screws with this particular kind of head, or the capability to be able to work underwater without rusting, and so on. We don't make a screwdriver that doesn't rust for that reason. We make the screwdriver to screw screws, but with the capability not to rust. Every manufactured entity has at least one function, usually exactly one function, but they may have hundreds of capabilities. No piece of material, raw material, has any function, but once it's been used in some kind of artifact, it will be part of something which has a function, and it itself will have capabilities. All right, now, once we have capabilities in BFO or in a mid-level ontology which links to BFO, then we will be able to extend IOF into areas like human capital ontology, expertise ontology, employment ontology. There are already experiments along these lines which are being carried out by members of IOF working groups and also by people outside the IOF. And the ones that I'm interested in, of course, are the ones where the experiments are being carried out on the basis of BFO, because then we will have at least the opportunity that they will be interoperable. If people are building an expertise ontology which is not based on BFO, then it will be a matter of luck if it fits with what the work the other people are doing. And at the moment, BFO is as it seems, is an attractor for people because it brings benefits that there are skilled personnel who know how to use it, skilled personnel who recognize BFO ontologies and who know how to identify problems, and so forth. All right, now roles, this is a picture of dispositions. So capabilities and functions are both dispositions. That means they are features of the entity which depend upon the physics of the entity. And so if we want an entity to have a disposition of a certain sort, we need to change the physics of that entity. So if I want to make CERM a fearful person who is afraid and weak, I beat him up a lot. I change his physics so that he will be a weak person, for instance. But now roles are not a matter of physics. If I declare CERM to be the smiler in chief in this room, then he has a new role, but he doesn't change his physics at all. And so the role side of BFO has to do with things like authority and promotion and employment contracts and so forth. All of those have to do with people changing their status is a result of some kind of social assignment. Once they change their status, they will change their physics too. Once CERM is assigned the role of being smiler in chief, that means his physics will change. His face will become tired every day because of all the smiling he has to do as part of his job. All right, now these are the existing IOF working groups which are meeting regularly and which are contributing content to the release versions. We have 3 release versions already, which you can find on the IOF website, which is down here. One for the core, which I've just talked about, one for supply chain, and one for maintenance. The others are all works in progress. You're happy to join any of the other working groups. You're certainly happy to see the results of the working groups thus far. But most importantly, you're happy to propose new working groups in order that you will serve as an attraction point for the people working on ontologies in your area who want to be part of the IOF effort. Now, this effort models the effort that we already have in the biology world, which after 20 years and something now like $4 billion of investment is a really thriving effort. And we're trying to create a parallel thriving effort now for the industrial domain. And that's that. So I'll go and sit down.
Okay, thank you, Barry. Is there, there is some time left, so I will ask if you have any question to Barry, and then if you want to make any comment, want to have a short discussion, not too long, you can do it now. Is there any question? Yes, go ahead.
On rights.
Will you, is it like he needs to come down?
I think that yesterday people at home could hear it.
Okay,
but
perfect.
maybe can people at home hear the questions in the room?
Just to ask you about the rights, as you said, as an abstract, just for my understanding, because on the whole, what we're talking about a license is a concrete.
Yes.
Okay, I mean,
Yes, so
but it's not abstract in the sense of thought or something.
I don't like to do philosophy, but at this point I have to do some philosophy. So in the history of philosophy, there were some people who believed that the only things which exist, Plato, for instance, the only things which exist are ideal entities outside space and time. There are other philosophers in the 20th century who believe that the only things which exist are real entities, which are part of the causal world and which change in space and time. Now, the school of thought from which BFO derives is a radical school of thought in the sense that it believes what is obvious, actually, that there are some abstract entities which are not, have no molecules, don't change, but which have a history. And licenses are one example. And so licenses are neither Platonic ideal objects, nor are they material objects. They are objects of a third kind. And all of these IP rights, obligations, permissions, claims, they're all objects of the third kind. And BFO made room for them from the start.
Okay. Any more question? No, then it's okay. Yeah. Okay, so I will bring in Sylvia now. Sylvia will talk about the progress in one of our tasks in the work package 3, which is review of domain interoperability. Sylvia.
Hello, everyone. So what I'll briefly do here now is to give a bit of introduction to this session and also give the context to what we are doing within OntoCommons in this direction and why we would like your input in the following session. Thanks, Christine. So, so with Arco and with the working group from the project, we prepared this. So it's about the review of domain interoperability, which is, what is it? It's a deliverable that OntoCommons will produce at the end of the project, so by November this year. And the idea, it will be a review of semantic interoperability, especially data interoperability via ontologies, but also in the broader sense. And the aim is to provide guidance to developers of domain ontologies and domain-specific assets, tools, and components in the area of materials and manufacturing. So it will include pointers to classifications of interoperability, principles, recommendations, technical solutions, and scenarios, and advice from OntoCommons and from the wider community. So we saw yesterday, for example, in some talks, that there are different levels of interoperability, and this can be helpful to position yourself in your work, to know which levels you're focusing on. So the domains, what domains do we address? So you see here some working groups we have that are active at the moment. So we have, within the industrial domain ontology group, we have system engineering, material science, manufacturing, product and service, and maintenance. These are the currently active ones. And the aim of this session, which Barry just started, and we go ahead also after the coffee break till lunch, is to have brief presentations and interactive discussions and gather your input and feedback for this work. So we have, within this group, we have split the work into three. So we have a working group 1 on terminology classifications of interoperability, second group on the technical components that support it, third group on scenarios. And so here you see the flow of information from one to the other. And now in the following, I'll briefly show you some extracts of the current results. So when it comes to interoperability scenarios, our colleagues, thanks a lot to the colleagues in the demonstrator package, they did an analysis of all the demonstrators to see what is the interoperability perspective in them. So they answer this sort of questions, like, for example, what is the interoperability pain in the use case? What kind of systems are you... Can you hear me? Okay. Okay. And so on. So, for example, here you have an extract for the Airbus showcase where, data processes and humans are the focus, is cross-domain, and there are heterogeneity types are syntactic, terminological, and conceptual, and so on. And then to try to classify the different scenarios, we followed an approach from the EIC. So what is the purpose of the interoperability? So is in this case, understand, find, operate, and update. So we try to organize all these scenarios in this framework. So many thanks to WP5, really. So this is another extract of, so we have been collecting initiatives and activities that are relevant for interoperability between domains. So here you find a list. So, and we, for example, the data documentation initiative cross-domain integration is one, just to give you an example. And so we looked for initiatives that are Europe-based, worldwide, and so on, and in different domains, as long as we can reuse some of the results for our domains. And so, of course, one thing we would like to ask you is to point out initiatives you are aware of in this line. And another type of result is, as I told you, there is a working group on interoperability terms and flavors. So terms related to interoperability, we found an extract is, for example, alignment, compatibility, heterogeneity, integration, mappings, semantic conflict, and so on. And when it comes to flavors and types in the literature, we found many. You can see here an extract. And of course, a caveat is that they are not all in the same bucket, so to speak. So you can recognize some are very popular, some are less popular, like, I don't know, diachronic and synchronic interoperability is more special. But so we found many different flavors and concerns. So the idea is that, there are many concerns depending on your point of view. And of course, one has to be careful when comparing them, but we think it is useful to be more specific when one talks about interoperability. So interoperability of what, at what level, what do you mean, and so on. And for the technical components, so we have identified that the high architecture level, some of them, so for example, those marked with a star come from the Data Spaces Support Center project, and they are called building blocks for data spaces. So you have data models and formats, data exchange APIs, provenance and traceability functions, and so on. And we identified others, but we will ask you later what are, according to you, the principal components, technical components that are needed. And so this is just to give you a flavor of what we have. And here is a brief list of some aspects that we are addressing, and also the speakers of the session have been asked to consider. So as I said, definitions of interoperability. So what the definition do you use and follow? What classifications, types, flavors, related glossaries, to be more precise, when we talk about interoperability, which metrics? So do you use any metrics or tools to assess the interoperability of data? Do you use anything to measure its maturity? What dimensions are important where you want to assess different solutions? Principles and recommendations, as for example, generic principles, set of principles, foundational principles, as long as, again, remember, we're in the context of domains, so we're interested in implications for the domain level. And then, solutions and frameworks you might be aware of, technical components, as I mentioned, and then both intra and inter-domain, so how to facilitate it concretely. So, for example, a typical question is like a domain agnostic approach can really support cross-domain interoperability. And yes, the difference between actually technology at research level and then actually its uptake in practice versus theory, let's say. Yeah, state of practice versus state of art. And how to actually integrate all these results in your existing workflows, which is a typical problem. You have an existing workflow and it's very hard to integrate something new. And another topic we will discuss are standards versus ontologies, whether there should be alternative solutions or they should be combined. And finally, a topic that is very timely, which is like, what is the role of large language models? What role can they have today and what they can have in the future? How is best to combine them with semantic technologies? And with this, I thank you for your attention. Thank all the colleagues. And if there are any questions.
All right, thank you, Sylvia. So this will be our topic for the next session after the coffee break, and we will open the floor for some interactive discussion. But now I will bring our next speaker, David Cameron. And while we are getting the slides ready, David Cameron is the manager of external engagements at the Design Center for the Data and Computation Science at the University of Oslo. He's a chemical engineer with a PhD from the University of Cambridge and experience in the industry and academia, and his research interest is computer-aided engineering, operation, and chemical process system. David, the floor is yours.
Cameron worked at the University of Oslo here with a research program talking around digital twins. So I say next slide to get next slide, is that right? Okay, yes, David Cameron, University of Oslo. What I'd like to do today is present a industrial case study which has linkages to ontologies and it demands on ontologies that I'd like to offer as an example of what we can try to do as a use case to get ontologies in place. The actual context is a substantial investment by two Norwegian oil companies, two Norwegian engineering companies, to try to work out how we can use and exploit information modeling and ontologies to make our field developments, making oil platforms better. So they committed money from budgets of this development, which used to be called NOACA, which was an acronym for a lot of oil fields, and is now called, in good Norwegian style, Yggdrasil, which is a reference to Nordic mythology. And what we're trying to do here is that they want to exchange and share the engineering data along the design process. And that's about trying to digitalize and make interoperable certain engineering artifacts that describe what the system is doing. Next slide, please. And what I'm interested in is digital twins. I'm interested in trying to create applications that enable you to make sensible decisions about some system or object of interest that you have to make sensible decisions about. And those sensible decisions have to be based on knowing what the current and possibly predicted state of that particular system of interest is. And there's three things that you can build that upon. The first thing is you can observe the system of interest. You have measurements or data on that you can go and observe. You then have mathematical or logical descriptions of how that particular system is behaving. And you then have data around what this particular system of interest is built up of and what its design rationale is and the static information about that particular system. And we want to build these sort of things, and we believe that information modeling is an essential aspect of creating this particular type of framework for digital twins. Next slide, please. So our approach is to model the process in a top-down way so that we can take the requirements that we have on what the facility that we're building will do and what sort of equipment we will use to build this facility in a structured way so we can link requirements to information objects at the correct level of granularity so that you don't lose those requirements when you go down and create your engineering documentation. And so this is about, primarily in the first instance, modeling firstly the process that we wish to do on this particular chemical plant or oil platform. And we do that in a top-down way at very lower levels of physical abstraction, starting with a big box which says, I am an oil platform, and I'm going to do these things, going down to eventually down to small process units that do specific things like separation or pumping. And then when you get down to that level, you then ask the question, well, how do I actually physically realize these things I want to do with the facility? And then you can purchase and install items that correspond to these specifications that you've given into an installed system. So I'll go into this detail a little bit more. Next slide, please. Related to this is also a description of what is a system. We've adopted a systems approach to doing this, and we believe it's very fruitful. But what we see is that systems in 1596 Part 4 and BFO are very much assemblies of potential physical things. In the systems engineering approach worlds, where I think the premise is that systems solve all the world's problems, the system abstract idea is a lot more abstract, and it becomes a sort of way of analyzing some sort of desired reality. And then in the middle, there's a standard called ISO 81346, which has an each way bet. It can describe a way of analyzing reality, or it can describe an assembly of things that do something together and have emergent behavior. Next slide, please. The particular domain we're looking at is the chemical engineering design of a facility. And chemical engineering looks at things in a very system way. And what we want to do is do a mathematical analysis of these systems. So this is a description of the type of modeling that you can do of systems. And you can start at a very, very low level, and you can model up at the enterprise or universe sort of level about what we're trying to do. What we're interested in building a chemical plant or an oil platform is a mathematical analysis of reality around the sort of scales where we're looking at from particle size up to the size of an oil platform. And those are the time constants and length scales that we're looking at. Okay, next slide, please. one thing we also see is that our information models must support different concerns. And we also capture information at the stage where we're doing design, where the facility that we're designing does not exist, that is going to be very valuable to us when we're trying to analyze the behavior of the actual facility when it does exist. And what we see is that there's a group of professionals who are very, very interested in what the facility is doing, what its process is. And they're also interested in doing that in operations. And so when we design, we start off by saying, well, what will the facility do? And then the mechanical and piping engineers go in and specify, well, what do we actually need to build to achieve these things? In operation, the mechanical engineer is saying, now I need to make sure that the things that I've bought and installed are behaving as they should as items of equipment. And then the process engineer and the process manager is saying, yes, but is the whole system behaving in the ways it should, fulfilling the process requirements that we put on when we actually designed a facility? Next slide, please. And this distinction between process and equipment was actually a foundation for the development of the entire discipline of chemical engineering. 150 years ago, there weren't chemical engineers, there were industrial chemists and mechanical engineers who went and built bits of equipment that did certain things. And that was great, but what you had there was that there wasn't the ability to scale up and mass produce what you were doing in a chemical industry. And this man, Arthur D. Little, who's now got a very large consultancy firm named after him, created this abstraction, the unit operation, the description, mathematical description of a process that then could be realized by equipment. And that created the discipline that I come from. And we need to maintain this abstraction between process steps where you're actually saying things about the qualities of it. You're asking how much is happening, how fast, how efficient, how near to completion, and how pure, which is then realized by what we call plant items, which are typed by a noun, and they're things, artifacts, physical objects, pumps, process columns, pressure vessels, and valves. And you say the usual Finnish things about those, how heavy they are, what they're constructed of, which product you're going to buy to fulfill that role. So next slide, please. So what I was asked to do was to create a semantically informed interoperable representation of a artifact which is called a process flow diagram. And so this is if you go into a chemical facility and you try to understand how the facility works, they'll give you this diagram. And it looks like lots and lots of equipment connected to each other by streams. Well, not quite. What we've got here is actually that the picture here of, for example, a distillation column with a stripper label on it is using the equipment as a proxy for a process. And so what we're doing at this stage in our design, when we're defining these sort of diagrams showing how things work together, are actually connecting together system objects that represent functions, the intended function of the assembly of equipment that we're going to be building in these places. And what we did was to do that, we then created a library of system blocks using your favorite object or port building tool. I chose, in this case, SysML as being a relatively cheap and effective tool that enables us to model these sort of artifacts. And then we have worked with the DEXP initiative to propose a standard set of blocks to build these sort of systems. So can we move down one more slide? And so the DEXP Plus and the IMF framework we're also working with, which Dextry Plus inherits from uses a pretty well-known object-oriented paradigm for modeling process steps. It looks at things as a system, and that system can have places where it can interact with the outside world, ports, and there's certain ways of interacting with the outside world. You can send out material with a certain structure, you can send out energy at a certain rate, or you can send out information, which will then be used by some sort of control system or decision process around this particular system. And then we also simulate also the activities you will need to do in your control system to make this whole system work. Next slide, please. And so what we've created is a hierarchy of process steps. We need a taxonomy of the things that you want to do when you're processing materials in a chemical facility. And so we start off with a hierarchy of that, and we've been able to draw on what was in ISO 15926 Part 4, but we have also a hierarchy there where you talk about top-level process steps, which are saying we want to separate material, we want to transport material, we want to compress material, we want to pump material. But then when we're doing this sort of thing, we also need to link what we're doing to certain physical processes. And so we ask that we want to do separation by distillation, or we want to do transporting in piping, which will have different constraints on it than transporting in an open channel. Or we want to do compressing by centrifugal motion. And we need to capture these physical principles because they have implications for how we actually model and describe the processes we're working with. Next slide, please. And so what we've done is we've said, good, we've got this artifact. That artifact is a view in on a very complex reality, and at present there's no single source of truth there, and so a lot of alignment between what you have represented on that diagram and the rest of design is kept in people's heads or in documents. What we want to do is create a model where we can explicitly make linkages between equipment and processes and ensure that we maintain these linkages and requirements. And so what we've done here is that we've taken that existing physical artifact and extracted out the model of processing steps that we need to do with the flows of material between the processing steps that enable you to abstract out of that what is actually happening and link on requirements we want to make about the performance of the system onto these specific objects. And then you can link that up to what you're going to construct in practice. Next slide, please. So our model is not a semantic model, but it requires semantics to make it interoperable and make sense. So our process steps are what was Barry saying, the primary intended function of the thing that we are eventually going to try to specify to fill up that function. And so we need verbs which describe these. Now, the physical objects is the area where ontologies in the process industries have been very strong. Large catalogue of things you can use to build together to fulfill these functions. But there's no one-to-one correspondence between plant items and process steps. A pump realizes a pumping process, but it only does that as part of an assembly of piping and things. Yep, soon finished. A pressure vessel realizes a separation process, but again, only as part of an assembly. And what we also see here is we've got a semantic shift where you say, I've got a separation process, but the piece of equipment that realizes it is not a separator, it is a pressure vessel with a role of doing separation. Now, we need qualities to represent the properties of both process steps and plant items. And those are things like temperature, pressure, mass flow, composition, Energy flow is absolutely essential. Everything is measured in kilowatts and heat transfer coefficients. And we also need to make our attribute models non-fragile. All too often, interoperability standards go in and say things about what they want to specify. What we want to do is our models is say, I have a process or a thing. Here is a physical or design parameter that I can say lots of things about. So I don't say, I don't have an attribute design temperature on my object library. I have a temperature. And then you can start saying lots of things about that temperature. So you can say a specified upper limit design pressure. And then we can have a taxonomy of things you can say about parameters. And that is a way of actually making our models less fragile. Next slide. So that's basically what I wanted to say. It's a very fast presentation, unfortunately. And what I'd like to also say that one of the major difficulties we've had with this work is that there are so many words which have about 8 or 9 different meanings, depending on who you talk to. And so the whole issue of what is a product. My product is the oil we're making. The valve manufacturer's product is the valve they give us. ISO 81346 talks about product as the equipment you actually have in the facility. Same with function, process steps, and streams. So all these words, there's a warning. If someone uses them, you have to ask what do you mean by them. Anyway, thank you for your attention, and I'd like to take any questions. And thanks, guys.
Thank you, David. We'll take the questions in the end. I mean, but we are running a little bit short of time. So we will bring in the next speaker, Francesca Blanken, who is a research scientist at SINTEF in Norway. She has a background in both experimental and computational chemistry, mostly in the field of heterogeneous catalysis, and has a PhD in physical chemistry. Her interest in the field of making data interoperable is mainly from the data scientist perspective. She is coordinating she has a coordinating role in the SINTEF team, developing a stack of tools, especially for interoperability.
Thank you. So my talk is called Interoperability Enabled by Data Documentation. And it's really about how we have all these different systems that are disconnected. Here you have 6 systems that all have one-on-one connections. And if we want to add in a 7th system, we have to make an additional connection. So we're talking about ontologies, and we're going to talk a little bit more about what is needed more than the ontologies. We can go on, please. So yeah, the thing is we have to make our data fair, findable, accessible, interoperable, and reusable. And you all know these words, so that's nothing new. But I want to stress that what we think is important is that we have to document your data. And we have to specify what does it mean to document your data, because if it's not well documented, no one can reuse it and understand what it's about. Go ahead, please. So there were some questions that were asked, that we could send some questions before the presentation, and one was about interoperability and what we mean with interoperability. So I put up a sentence at the top there, borrowed from Wikipedia, but I think it's quite fitting. Interoperability is the ability of computer systems to exchange data with unambiguous shared meaning, which means that you really have to understand what we're talking about. Now we can share information, share knowledge at different levels. We can have all the way up at our human level, the high abstraction level, where we talk about how an equation describes something in the physical world, etc. But then you go all the way down to the numerical level, where we're talking about what we need to actually exchange when we exchange data, and those are the numbers. And ontologies play a very important role and are necessary to make sure that we understand what we're talking about and we're speaking the same language. And then in addition, we need this small interoperability framework at the bottom here, which helps us really exchange the numbers and the data. So please go ahead. We can have different levels of interoperability. We have compatibility at the bottom here to the left. There are two boys who have constructed their own little telephones. They work very nicely. They are living in the same world, and they have no issues understanding each other. Then we can have a bit more sophisticated telephones where we have connected them to the switchboard, and the old lady here, she's talking to her grandson. He understands Norwegian as she's speaking, and they speak very well together. Now we need to add semantics to get semantic interoperability when they cannot speak the same language or are not living in the same context anymore. So we really need this. Yeah, okay, please go ahead, that's fine. Human communication, we need to have the common language, and we know that. You're talking about ontologies, all of you. I just like to stress, this one is a nice one since we're in Norway, because in Norway, if we say grine, it means to cry. If I talk to my Danish colleague back there, he's going to think I'm talking about laughing. So even if we humans, as you just pointed out before, David Cameron, that words have lots of different meanings, this is, of course, the same also for humans. And it's really, really, really important for a computer to understand because they don't understand the context. I can understand the context. We need to provide the context in some other manner. So please go ahead. Tools for communication, we have the language, the ontology that gives us the language, the description of the world. But in addition, we need to have some additional tools that help us send that language around and send the meaning around. So we humans, we have a mouth, we have brains to understand, we have ears to hear. The same with machines, we need to have a set of tools. And I'm going to talk a little bit about one part of this here. So please go ahead. Oh yeah, so this is the PDF version. Is it? No, that's fine. I'm just because now then it's going to have things on top of each other eventually. But okay, that's fine. If we look at the top here, we have two sets of people. To the left, we have one person saying, I want other people and machines to be able to use my data because my data is so good. You have to understand, I want to give it to everyone. Okay, then you have to make your data fair. Okay, what does that mean? Or the other one, the right here says, I want some data. I have a model and I want to do some simulations, but I need some input. Okay, document what you need. So if we look at this figure at the bottom here, which comes from the Materials 2030 roadmap, you can see this big chunk here, which is the documentation. And this documentation contains a lot of different things. It contains cataloging, it contains structural documentation, contextual documentation, and semantic documentation. And all these are needed for the machines to understand what is the data you're sending me about. So if you go ahead. So first of all, cataloging, that's something we already do. If you need to know where the data is, and you need to have some extra metadata on who can use it, etc., etc. Please go ahead. And you have structural documentation. And here we make use of something called data models, entities that are based on a data model ontology, which are very simple ways to describe our data close to how the data is represented. So that means that if I have an Excel sheet and I work with Excel, I can make a data model that is close to that Excel sheet. In this particular example, which is see here to the left, a table format of it, we have an alloy. This is a data model for an alloy. The data model has a certain number of elements, and then we know that the elements, we need to have to know which of these elements, which elements are. These are the properties. We have to know the composition of the elements, and then we also have the density of this particular alloy, and that's what is contained in this data model. And in the middle one, here you see the serialized JSON. Serialized as JSON, it's just simple for the machine to read. And just as an example to the right there, you have an instance of a populated one, also serialized in JSON, but it could be anything else. So we have this methodology to describe our data in a manner that is close to our data source. If you go ahead. Yeah, so this is messy because it was supposed to happen one by one. But the point here is just that the Contextual documentation is contained in a knowledge base, and this is very, very important because we have to understand where our data from. In my case, let's say that I've done some calculations on a particular structure, but I don't know where they come from. They do not have very much value. But if I know that they come from a certain measurement at the TEM machine at SINTEF in Trondheim, then I can know more about the material, and I know what I'm doing calculations on, and we can put all these things together. So the contextual documentation is extremely important. If you go ahead. And then finally, the semantic documentation. So we have made these data models, and here you have two examples. One to the left is the tensile measurement, and to the right, the structural model. These are two data models. And they describe the data to the left, the data that we have or someone has, and to the right, the data that exists. No, that I want, sorry, that does not exist, but that I want. I want to populate such a data model. If I have made the data model well and then done the correct mapping to the ontology, I can use the ontology and traverse the ontology and the functions in the ontology to populate the number that I want. So for instance, here I want the yield strength. This is not something I have, but it matches to this yield stress in the ontology. There is a function that can get this from true stress and true strain. These are also two values I do not have, but you can traverse further and further until you finally get to a point where you have the values that you need to actually populate the other structure model. So if I have documented well what I want and mapped it well to a good ontology, then we can do this traversal. So please go ahead. So how do we actually do that? We do that with something called reusable partial pipelines. So for each data source or data sink or model, we have to provide information about access, that's the cataloging. We have to provide information about how to parse the data, or in the other case, to generate it if we want to have it as a data sink. And that means actually making these data models. And then we have to do the mapping, which is the mapping to the ontology. And once we have these ones alone, they describe for each sink and source how to get that data or how to put data in there from the common interoperability framework. If you go ahead. And that doesn't make, okay, this was supposed to be come up one and one, but if you see at the back here, you have two yellow arrows for the yellow data. There you can have the partial pipelines for that one. You have the red one. You also have some partial pipelines for how to get that data or have to put data in there. The same for the green and same for the blue. Now, with these partial pipelines, they don't really work alone. They have no meaning alone. But if you put them together and say, okay, I want this one at the right, and you say, okay, you can use this one and put it together with one that provides data from somewhere, then you get the full partial pipeline that works together. And by using the ontology, you actually end up getting the data that you want. You can go ahead. So this is a framework for data documentation. You have at the right, here again, this person asking for something or a computer asking for something, and you can generate that if you have the correct documentation of what you're asking for, and if you have the mapping to the ontologies. Go ahead. Now, this requires a lot of work. I often hear in these areas, everyone's talking about how easy everything is. Once you do it, it's easy, because I have a good data model and we do it ourselves. We also say that our data models are easy and simple. But it's not necessarily so simple. So one thing that we think is good about this approach is that it gives the possibility to also separate the concerns a bit, so that the person that is very close to the data provider or the modeler, can describe his or her data models in a manner that is close to the data. And they don't have to think too much about ontologies, etc. But they need to have a very good interaction with the ontologies that can help make the ontology if the ontology is not there, or help map to the ontology if it's already there, or do both. And then you also need some help maybe from a software engineer to make some parsing strategies, etc. Then go ahead. So yeah, okay, that was it then. But so if we have this possibility of attaching to one underlying interoperability framework, making use of the ontology at the bottom, then we have the possibility to attach a new computer system to the same system that all the other ones have been connected to before, and they are automatically interoperable. I think that's it. Thank you.
Thank you, Francisca. So I'll open the floor for any question for David and Francesca, and also, query if you want. Though the coffee is ready, so if you do not have any question, we can directly go to the coffee, but I'm not insinuating anything. Please ask any question you have. Okay, so everybody wants coffee. That's the verdict. Okay,
Yes,
let's go.
there was a question from Francesca, but for the previous presentation. How does your hierarchy of process the decision with respect?
Is this for David?
No, it was in the first presentation.
No, process step was several.
Let's
Yeah. It's a question for David. Okay.
What we found was that we're not using the manufacturing industry's functional basis or VDI. What we have done, however, is taken a basis in the process industry standards the Germans had a DIN standard to describe this material. Chifos and Dexby have had their particular takes on ISO 15926 that has been the basis of that. The modelling we've done is chemical process functions, and those have their own vocabulary. And what we've been doing there is defining and going around picking the existing standards so we get a vocabulary that people can agree on.
Okay. Is it?
No other questions.
Okay, no other question. Hopefully it was satisfactory. And I will end this session now here, and then we'll go for the coffee break and then come back. Please try to be a little bit in a hurry, and then because we have an interactive session to do, and which will be very exciting. Thank you so much.